Hello everyone. Today we will learn about the types of discrete random variables. But before we go to the types, we will see a brief review about discrete random variable and also the concepts of mean and variance in random variable. Uh, in previous video, we have learned about the definition of discrete random variable. And here is an example of discrete. Uh, there is a bank which counts the number of credit cards carried by a group of customers. And they put the result on this table. The first column is for the number of credit cards. There are 0, 1, 2, 3, and the last class is 4 or more. And here is the relative frequency of each its numbers. I mean, for example, 0, the frequency is 0.03, and then 1 is 0.1, and so on. Yeah, here is an example of discrete because the number of possible values here, the number of possible values is finite, right? There are five classes here, or five little x here. So this is a discrete random variable with a probability table like this table. And then yeah, we introduce two quantities here, the mean and the variance of the probability distribution. Here there is a note here. These two formulas are used for discrete. So this is only for discrete. Because if we talk about continuous random variable, the formula is different. Yeah, we start. The first is mean. Mean represent the central location of the data, and also it's also referred as the expected value. And if we see here, the mean of probability distribution is denoted by mu, and it's defined to be this sigma. But I think I will write with another formula. Suppose that our possible values of this random variable is x1, x2 until xn, like this. And if we rewrite the formula here, it becomes mu is equal to sigma of x subscript I times the probability of x the probability of x little x subscript I, where I runs from 0 until n here. Yeah, if I rewrite, it becomes this. And actually this mean is a summation of this multiplication xi with its corresponding probability. Yeah, like that. For example, here in our previous example, now suppose that this is the x1 maybe, and of course this is the probability of x1. Suppose that it is x2, this is the probability of x2. So we multiply this x with its probability. Multiply this, multiply 0 and 0 0.03, 1 and 0 0.1, 2 with 0 0.18, and then and so on. And after that, we add all multiplications. Yeah, later we will see how to implement this formula. Yeah. And then actually this complicated formula is actually the generalization of the mean in the mean in data in our non-group data. It's actually the generalization of ungrouped data. And then to count the variation of the spread of the data, we describe or we define the second quantity is the variance of probability distribution with symbol sigma square like this, and it's defined to be the sigma of open bracket x minus mu, where mu is the mean. We square this term, and then we multiply with the corresponding probability. So if I rewrite again with this, it becomes sigma square equal to the sigma. Of course, the sigma is from 1 until n, and then we write like this: open bracket x subscript e minus mu, the mean. We square them and then multiply with the probability x like this. Yeah. This is the variance of probability distribution. As you can see, it's more complicated than the mean, and we need the value of mean before we determine the variance. And the third is the standard deviation. It's similar with the ungrouped data. The standard deviation is the positive square root of the variance, or we can write the standard deviation to be the value of sigma. Yeah, these are three quantities: the mean, the variance, and also the standard deviation of the discrete distribution. And once again, this only for the discrete case. Okay, let's move to our example to illustrate the definition of mean and also variance. Let me use again our previous formula. Let's move like this. Yeah, and also like this. Okay, let's start with our table first. In this table, we will see the number of cars sold denoted by x, little x here in the first column, and also its probability. The first is 0, 1, 2, 3, and 4. And if we label those variable, or I'm sorry, if we label those x, we can write 0 to be x subscript 1, x subscript 2, and so on like this. And the last is x5. And of course, this is the probability. Okay, first we need to find the expected value or the mean. We use the because the number of x is 5 here. Of course, this is a discrete case, and then we can apply this formula. Mu is equal to the sigma of multiplication xi times its probability. So we multiply 0 with 0.1, and the result is also 0. And then 1 with 0.2, the result is 0.2. 2 times 0.3, the result is 0.6. Next, 3 times 0.3, and the result is 0.9. And the last 4 times 0.1, and our multiplication is 0.4 like this. And then don't forget to sum up all of them, and then we can get the value of mu is 2.1. So the expected value of the number of cars sold is 2.1 here. And then I think we have done with the mu here, and then we can use this mu to find the value of variance. Okay, next let's see about variance like this. Yeah, probability. Yeah. From the let me see the formula of variance sigma square. We need to find xi minus mu first, and then we square them. Okay. Let's add a column here, x minus mu. We subtract 0 by 0. I'm sorry, we subtract 0 with 2.1. It's our value. So our mean 2.1 here. 0 minus 2.1, and then 1 minus 2.1, and so on. Yeah, after that we squared them. If I will only illustrate for two cells here. This is equal to negative 2.1, and if we square this value, the result is 4.41 like this, and it is minus negative 1.1, and the square is 1.21 like this, and so on. You can continue it by yourself, of course, and then don't forget to multiply all this value with its corresponding probability. So to get this, for example, to get this, we multiply the probability 0.1 with the 4.41 like this. I'm sorry, 4.41 like this, and the result is 0.441 like this. Yeah, and you can do similar thing with the next cell, and if you sum up them, the value of sigma square is 1.29 like this. And of course, if we want to find the standard deviation or sigma, we can take the square root of 1.29, and you can get the value of sigma. Okay. Well, I think this is a good illustration for mean and also the variance, and yeah, and the standard deviation. Okay, we have done with our first section, and next we will go to the types of discrete random variables. In this video, we will talk about 3 types. The first type is the binomial distribution, and the next is hypergeometric, and the last is the Poisson. And let's start with the binomial first. Before we go to the formula, let me see what is the requirements of a binomial probability distribution. And once again, this is only a type of discrete random variables with special features, special properties. The first requirement is we have only 2 possible outcomes, and those outcomes are mutually exclusive. In general, we can classify those 2 outcomes to be the success side and also the failure side. Yeah, maybe you can, maybe in the case of head and tail of a coin, you can define success to be the the head and the failure with the tail, like that. As long as those outcomes are mutually exclusive, it's okay. And then the next, we have we have fixed trials, fixed number here, and the probability of a success is same for each trial. So in the first trial, the probability of success is maybe suppose that in the first trial, the probability of success is a little p, and the next is also equal to little p, and it happens to be to all trials here. And the last is our each trial is independent of any other trial. It means the outcome of one trial doesn't affect the outcome of other trials. And here, I think we forget to define what is the definition of the random variable x. Here, the random variable is the number of success in a fixed number of trials. So we count the number of success like that. Yeah. Okay. If an experiment fulfill these four requirements, we can classify it into a binomial probability, and then we can use this general formula to find the probability of its x subscript I, like that. Yeah, suppose that x is an element of possible value. X is a possible value of x of big X, like that, like this. We can find the probability of little x is equal to combination of n x times this is phi. Phi is the probability of success on each trial, and this is only a symbol. Don't be confused with the phi as a number 3.14 blah blah blah. They are different. Phi here, it's only the representation of the probability of success here, and phi to the power of x times 1 minus phi to the power of n minus x. That is, yeah, this is the general formula of binomial probability formula. And let's see the example of the binomial probability. Here we have a report that said 28% of purchases at coffee shops were made by a debit card. And then we select 10 randomly purchases, and yeah, and then we need to find the probability. The first is the probability that no purchases were made by a debit card. So from this 10, the purchases are made by non-debit card. Okay, before we apply the binomial probability formula, let me see that, or let me check for requirements to be binomial variable. The first criteria we need, we only have two outcomes here. The first outcome is made with a debit card. This is the first outcome. Use debit card, and second is no debit card, like this. yeah, we have only two outcomes here, and they are mutually exclusive with debit card and no debit card. And then next, we also have the number of tiles is fixed, and we know that this number, of course, because we select 10 pieces, of course, this is the number of tiles. So our n here is 10. This is fixed and known. And the third, the probability of success is the same of each trial. We can see this third requirement from this report. 28% of purchases were made by a debit card. So this is our fee, 0.28. And the last is the tiles are independent. Yeah, I think it makes sense, because if we ask a person and he or she said, I use a debit card, it doesn't affect the second customer. The second customer can replay independently with his or her condition, of course. And yeah, we checklist the four requirements. And I'm sorry, I think we also need to see that the random variable x is the number of success. Here the success is using debit card success, and here x is the number of success. Like this, and then also the first, the probability no purchases made by debit card. Since our x is the number of success, or the number of using debit card from 10 customers, our x, our possible values are 0, 1 until 10, like this. And in this question is associated by the little x equal to 0, because no purchases. So substitute x with 0 here, p0. Here n is 10 combination 0 times 0.28, our fee here, and the power is 0, and then multiply by 1 minus 0.28 to the power of 10 minus 0. Just substitute x with 0 and n with 10, and this is the result is 0.0374. Yeah, we have done with this. And next, maybe another example is the probability of exactly one with debit card. So we talk about x equal to 1 here. So substitute x with 1, and we have this. I don't forget to subtract 10 by 1 here, because the general formula is like this. And then after we calculate the probability, the result is like this. Yeah. And of course, because our x can be 2, 3, 4 until 10, you have another result. Yeah, and if we make the table, distribution table, it will be like this. And then if we transform it into the bar chart, it can be like this. And we have a follow-up question here after the probability table. In this case, we can ask like this. What is the probability that 6 or more purchases out of 10 are made by a debit card? 6 or more. So it includes 6. If we transform this question, this is the probability of the number of purchases. The number of purchases is x. More 6 or more is like this. 6 or more. So, and as you can see, all you can see every x here, every 2x here is mutually exclusive. They are disjoint. So if we to find this, we can sum up the probability of x equal to 6 but plus x equal to 7 plus this and this. Yeah, you can sum up all these values and find the value of this equation. Yeah, we sum up from 6 until 10. Yeah, this is the result of this question. Yeah. And because the binomial and the variable is just a type of discrete, we can find its mean and variance. This is only the final result of mean and variance. The mean is n times phi, and the variance is n times phi times 1 minus phi, like this. And from the previous example, our n is 10 and our phi is this. And of course, our mean is 10 times 0.28. And if we see the result is 2.8. Yeah, you can use this shortcut formula to find the variance. Yeah, and in addition, we also have the binomial probability tables to help us in finding the probability of x equal to little x. Yeah, you can refer the table in Lynn's book. It's located on page, what is the page number here? 740. This is the binomial distribution table. This binomial probability distribution with this title, all values in the table is the value of this probability of capital X equal to little x, because the title is binomial probability distribution. And as we see before, our formula is like this, and combination x, phi to the power of x times 1 minus phi to the power of n minus x, like this. If we see, there are two parameters here. The first parameter is the number of n. I'm sorry, three parameters here, and a little x and also phi, the probability of success. To read this table, first of all, we need to find the right n. The first is n equal to 1, n equal to 2, n equal to 3. And in this table, I think there are some possibility of n. So if we want to find a probability with these parameters, and suppose that n is equal to 3, phi is equal to 0.5, like this, and maybe the first x is 2, maybe. So I'm sorry, with these 3 parameters, the probability of this first we go to the table with n equal to 3, n equal to 3. Yeah, this is the table, n equal to 3, and then we find the phi from the column. So the column here determine the value of phi. The value of phi we have here 0.5 here, and then we find the little x, the value of little x. Here the value of little x is 2 here, x, and then from these two points, from 2 go to the right, and then from this 0.5 go down, and yeah, our intersection is this value 0.3375. So by this table, this probability is equal to 0.375. Yeah, I think with this table we are easier to find this probability. But a problem happens if our phi, our probability of success is not exist in this table. Yeah, if we are in that problem, of course we cannot use this table, and perhaps we can use another tools like calculator or the Excel file. Yeah, this is just an illustration of using the binomial table to find a particular value. And of course, if we need to find p equal px equal to 3 with parameter n equal to 3 and phi equal to a half, of course you can go to the last row and then find the intersection. Yeah, just like that. Okay, I think we have done with the binomial, and the next is the hypergeometric distribution. In this distribution, we do sampling from relatively small populations, and in this case, without replacement. Okay, and we have 4 requirements here. The first is the outcome of each trial is only classified into 2 mutually exclusive categories, similar with binomial, success and failure. And I'm sorry here, our definition of random variable is the number of success in a fixed number of trials. Here we have fixed number of trials, and the trials are not independent. One trial affects another trial, and our population is finite and also without replacement, with the proportion of n divided by little n divided by big N is greater than 0.05. And here is the general formula of hypergeometric distribution. Suppose that our possible value is little x here. The probability is this as combination x. Here, I'm sorry, before that, let me illustrate the first. Yeah. I'm sorry. S is the number of success in population. And then little x, the number of success in the sample. So yeah, like this, we have a population, and also we have a sample S here, and yeah, the number of success is known. It's denoted by big S, and X is the number of success in the sample, and we multiply with n minus S, combination of n minus little x. Yeah, this is the failure side, and also we divide them with this value. Big N is the size of the population, and little n is the size of the sample. Yeah, of course, the size of the sample, little n, is less than or equal the capital N, right? Okay. To understand this hypergeometric, let we see the example. The example is in playtime toys. There are 50 people in assembly department, and we know that 40 of the employees belong to a union and 10 do not. So if we illustrate like this, now from 50, 40 belong to a union, and 10 not union. Yeah. And then from this population, this 50 population, we select five employees to be our sample here, only 5. Suppose that we label the 5 employees with this A, B, C, D, E, 5 people here, and we want to find the probability that 4 of the 5 belong to a union. So from 5, there are 4, exactly 4 to belong to union. And this is not union. Yeah, this is just an example, a case here. A, B, C, and E belong to union, and D do not. Yeah, here, and let me check first the requirements. Here, 50 is the number of population, so this is the capital N. 40 is the number of success, because we define success to be belong to a union here. This is capital S, and then 5 is the number of sample. Our size of sample is 5, and the number of success in the sample, or in 5 people, is 4, because we need to find 4 here. So for little x is 4. Let me check the requirement. The first, those outcomes, union versus not union. Of course, there are only 2, and they are mutually exclusive. I'm sorry. And then the random variable is number of success, of course, success. And our number of trials is fixed, equal to 5. The trials are not independent, and yeah, this ratio is greater than 0.05. Okay, this fulfill 4 requirements. So this is the hypergeometric distribution, and with this formula, P4 is as combination X 40 combination 4 times 50 minus 40 combination 5 minus 4 divided by 50 combination 5, and the result is 0.431. Yeah, if we can see in this hypergeometric, the number of success and failure are different. Success is 40 and the failure is 10. So the probability to be success is different with the probability to be failure, because the number of them are different. Yeah. Yeah. From this, of course, this P4 is only an example. You can try to find P1 because the sample is 5. The possible values of X is 0, 1 until 5. And with substituting X with 0, 1 until 5, we get this complete probability distribution. And the last type is the Poisson distribution. The Poisson distribution. This kind of variable describes the number of times some event occurs during a specific interval. And this interval can be time, distance, area, or volume. And we have two assumptions here. The first is the probability is proportional to the length of the interval, and the intervals are independent. There are no intersection between those intervals. And here, here we also assume that the probability of the event is proportional to the size of the interval. And yeah, I think it's the pattern is different from hypergeometric and binomial. Our probability of Poisson is our formula is like this, where mu here is the mean number of success in a particular intervals, and X is the number of successes. And this E is a constant with this value 2.71 and so on. And in Poisson distribution, our X can be infinite. So X can be 0, 1, 2 until blah 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 like this. And yeah, here by the sketchwork, the mean of Poisson is equal to n times v. Let me see an example of Poisson distribution example. In this case, an airlines called Budget Airlines, it operates flights from Myrtle Beach. And recently, this airlines has been concerned about the number of lost bags here, and Boston from analytics department was asked to study this issue. And to make the study, she randomly selected a sample of 500 flights, and she found that a total of 20 bags were lost in the sample flights. Yeah, we consider the flights as an interval here, And to find the probability of Poisson, we need the mu, the mean, and also the specific value of little x. Here our mu, the mean is found by this from 500 flights. There are 20 bags which were lost, and our mean is 0.04 here. And that we see the first question is the probability that no bags are lost. No bags are lost is associated with x equals 0, right? So the probability is p0. Just substitute mu and p and put it on your calculator and see the result is like this. And if we have this inequality, the probability that one or more bag is lost, or the probability of x greater than or equal to 1, we can use this complement formula to find the probability. As note here, because our all possible value is infinite, it implies that our sigma of px p subscript I, this I comes from 0 until infinity, it is 1 because the total of the probability in discrete or generally in a variable is 1. So if we sum up all probability, the result must be 1 here. And here, if we expand the sigma, it becomes this, and so on. Yeah, because we need this value, which is equal to this p1 plus p2 plus p3 and so on. Yeah, just move this term p0 to the left, so it is equal to this. Yeah, and just substitute, we have the probability is like this. Yeah, of course you can also find the others like this or like this. Yeah, by this complement rule. And for the Poisson, yeah, there's also a table here, similar with binomial, but yeah, it's simpler because there are only two parameters here for Poisson. The first parameter is the mu, and the second is x. So the columns here are the possible value of mu, and x here the possible value of x. Yeah, maybe we can use this. In this case, the mean number is 0.3. So we go to the third column, 0.3 here, and then we find the probability of no breakdowns. So no breakdowns associated with 0, right? We find 0 here, go to the right, and yeah, the intersection is this 0.7408. Yeah, other examples maybe with mu also 0.3, but we need to find exactly maybe two breakdowns here. Yeah, so we move to the third row, 2 here, find the intersection, and the result is 0.0333. Yeah, like that. I think this table is simpler than the binomial because we have less parameters here, only 2 for the Poisson. Yeah. I think I will stop here, and then you can try to do the practice problem here. Yeah, you can practice the formula in this lecture to find the answer of these questions. Okay, I think that's all for me today. Thank you for your attention. Hope this discussion is helpful for you and also for all of us. Okay, thank you. See you on the next video.